Okay, so in our previous video, we had taken a look at a set of parametric equations, two sets of parametric equations actually in our last example, each of which gave us the same curve. It was a circle centered at the origin of radius 3, it's just that the first set of parametric equations traversed the circle only once as t went from 0 to 2 pi, whereas the second set took us around the circle twice as we traversed our parameter interval. So what we want to do here is show how we could have known ahead of time that both of those would have given us the same curve without having to go and plot all those points and do all the work that we did. So this is going to be something that we call eliminating the parameter. And basically the idea behind eliminating the parameter is you have your parametric equation. So for our first one, we had x equals 3 cosine of t, y equals 3 sine of t, and then yes, we had that parameter interval, but I'm just going to use these two equations for now. What I want to do is find a way of taking these two equations and reducing them to a single equation that only shows the relationship between x and y, meaning the t is not going to appear anywhere. We're going to eliminate it. That's why we're calling this eliminating the parameter. Depending on the parametric equations, there's different approaches you take to eliminating the parameter. Sometimes you try to find a way of making a substitution from one equation into the other one. In this case, that won't really work. What we want to do here is use a trigonometric identity to eliminate the parameter. So notice if I were to square x and y, x squared plus y squared, and add them together like that, well, x squared is the same thing as 3 cosine of t all squared. And y squared is 3 sine of t all squared. This is the same thing as 9 times cosine squared of t plus 9 sine squared of t. And if I were to factor a 9 out, like this, sine squared of t, what's left in parentheses I recognize as my Pythagorean identity. That would equal 1, and so 9 times 1 would just give me 9. And so this left me with this equation, x squared plus y squared equals 9. That I recognize as the equation of a circle centered at the origin with a radius of 3, which is exactly what we got when we sketched this thing out long ways, okay? If I go to my second set of parametric equations and do the same thing, so, x equals 3 cosine of 2t, y equals 3 sine of 2t. I would do the same thing, x squared plus y squared equals what? 3 cosine of 2t squared plus 3 sine of 2t. And you're going to notice you're going to follow similar steps. Eventually we'll get down to something that looks like this. 9 times cosine squared of 2t plus sine squared of 2t. Now the fact that these are both 2t's here doesn't change the fact that we can use the Pythagorean identity. All that matters is that both of these arguments for this cosine here and this sine here are the same thing, 2t and 2t. This is still equal to 9, and so we still get x squared plus y squared equals 9. Same exact curve, which is what we observed in the previous video, okay? So that whole process there is called eliminating the parameter, because in both cases we ended up with an equation where the parameter did not make an appearance, but we did get a relationship between x and y in a single equation, okay? For the last thing I want to do, we're going to walk through a derivation of parametric equations for a specific curve called a cycloid. Now this is actually just copied and pasted from your book. So if you look in your book, that's why it says example 9 right here. I took it straight out of your book because the book does a fine job of explaining it. But the reason I like going through this example is because it sort of shows one of the ways that we come up with parametric equations for something in the first place. Like I had mentioned before, it's oftentimes really helpful to think of your parameter t as time, and to think of the corresponding points, the x and the y coordinates, as the position of a point that's moving as that time passes. So oftentimes we'll start with a curve that we don't necessarily know a convenient equation for. Like circles, x squared plus y squared equals 9, like in my previous example. I know that if I needed to find a circle of radius 3 centered at the origin, I know automatically that that's an equation for that. But something like this cycloid that we're going to talk about, it's not something we've encountered before. And one way of thinking about this curve is by thinking of the motion of a point in a very specific way. And so we can take that idea of how this point is moving and use it to derive parametric equations. So here's what we're looking at here. Imagine you have a wheel, right? Or more, mathematically speaking, just a circle. And that circle starts at some position on a horizontal line. So it's sitting on top of this horizontal line. And then picks some point on that circle. And we're just going to call that point P. What we're going to do is roll this circle along the horizontal line towards the right here and follow that one point on the circle that we've sort of singled out. As that point rolls with the circle, it's going to go up and down while this circle is moving towards the right. And so the point is going to make a path, if we trace it out, that looks like this. Okay, so if you follow the red curve, that's where the point on the circle is going as the circle continues to roll. This curve with all of these little arches here is called a cycloid. And it's got some interesting properties that we're not going to get into here. What we want to do is figure out how can we come up with parametric equations that describes or gives us this curve. Now the way that we're going to do it is we're going to think of this circle here, and we're going to put a little bit more detail on it. So for simplicity, let's imagine that the circle starts at a position where its point P is at the origin. So that would mean like the circle, if I roll this back a little bit, will start sitting right on top of the origin, and the point P that we're trying to follow along this path, it coincides with the origin. In this picture, the circle has rolled away from the origin a little bit. So if we follow that point P is going to have gone through this green arc right here as the circle rolled about this far. And because this circle is rolling on that horizontal line without any slipping, the length of that green arc is going to be exactly the same as this line segment on our x-axis right here, because that's what it has rolled through so far. So putting a few more labels on things here, here's the point P that we're following. Let's call C the center of our circle. The radius of this circle, we're going to just call it r. So the cycloid will depend on that r because it'll be bigger or smaller depending on the radius of our circle. And then if I take my center of my circle at whatever time that we're considering and drop a perpendicular from that down to the x-axis, I'm going to call that intersection with the x-axis t. Okay. I also can create this right triangle right here, where if I take this line segment from C to P and compare it to this line segment from C to T, I can think of the angle between those line segments as how far, or the angle by which this circle has rotated away from the origin. When we're at the origin, this line segment would have been the same as CT, but as we roll away from the origin, it's going to move this direction. Okay. So theta is a way of measuring how far we've rolled away from the origin, as long as theta is still less than 2 pi, because then it'll start to repeat on itself. So that allows me to create this little right triangle here with my radius and this horizontal line segment that joins the line CT. Q is going to be what I call where that horizontal line hits this guy right here. Okay, so on to the next page with all that stuff labeled, we can start to talk through how we would come up with a set of parametric equations. I'm going to try to do this where you can see both of them somewhat. Okay, so if you look down here, OT, which is this guy right here, is the distance that the circle has rolled away from the origin, but we know that that also corresponds to the length of this arc right here. So OT is equal to the length of that arc PT right here. And to find the length of an arc on a circle specifically, it's just theta times r, where theta is measured in radians. That only works if it's measured in radians. That's a fact from trigonometry. You learn that in the first or second week of trig, so we're not going to review that here. But that's how you would find the length of that arc, r times theta. Okay? Now, what we're going to do is we're going to assign P coordinates, x and y here. And the center of my circle, we're going to need to follow its coordinates as the circle rolls away. Notice that the center of the circle won't move up or down. It's always going to be the distance from the x-axis equal to the radius of this circle. So the y-coordinate of my center will always be the radius r. R times theta is going to be, remember, the distance from the origin to wherever the circle is at that given time. And that would correspond to the x-coordinate of our circle. That's the horizontal distance. So r theta is the x-coordinate right there, okay? That's what we're seeing right here. The center of our circle would be r theta r. And again, we're going to let P have coordinates x and y. I want to now find a way of relating all of these things. So I'm going to have to move up a little bit here. With all of that in mind, x is going to be equal to the length of OT minus the length of PQ. Why is that? Here's OT right here. Here's PQ. So if I take this and subtract this, I'm left with just this little piece right here, which is the x-coordinate of P, okay? But we said that the length of OT is the same as the length of that arc, r theta. And then what is PQ going to be? Well, again, we have this right triangle. PQ is one leg of that right triangle, and it's opposite that angle theta. It's easy to show from that the length of PQ is just r times sine of that theta right there. So r sine of theta. I can factor the r out and write that as r times theta minus sine of theta. That's the x-coordinate of our point P, okay? Y, I can find in somewhat of a similar way, TC minus QC. Where are those in our picture? Well, TC is this guy right here, and we're subtracting QC, which is this other leg of our right triangle, because that would leave us with this length right here, which corresponds to the y-coordinate of our P right there. So with that in mind, TC is r. Remember, that's the y-coordinate of your center. And then from the right triangle, it'd be easy to show that that other leg of the right triangle is r cosine of theta. So r minus r cosine of theta, which gives me r times 1 minus cosine after I factor that r out. This gives me parametric equations for my cycloid. So x is equal to this, y is equal to this, and we can allow theta to be any real number. That's what this notation means. There's a little blurb here that talks about how if you want to get one full rotation of your circle, that would give you one arch of that cycloid. So again, remember, the cycloid looks like this sequence of arches, but each one corresponds to one full rotation of that circle. So if you ever want to do something with just one arch of a cycloid, you can restrict theta to be in the interval 0 to 2 pi, because that would give you one full rotation. That's kind of what's being mentioned here. It also mentions in this little paragraph right here that you can eliminate the parameter, but you end up with this kind of nasty looking function of y down here, and it's not very convenient to use that. It's actually much more convenient in applications to use the parametric equations for this cycloid. So that's it for section 10.1. In 10.2, we'll start looking at the different types of calculus we can do with these parametric equations.